Lesson: Supervised Learning, Principles and Techniques. Supervised learning is a pivotal component of the machine learning paradigm, making it essential for professionals aiming to achieve the CompTIA AI Essentials Certification to have a firm grasp of its principles and techniques. In supervised learning, the algorithm is trained on a labeled dataset, meaning that each training example is paired with an output label, enabling the model to learn the mapping from inputs to outputs. This foundational approach is crucial for tasks such as classification and regression, which are prevalent in various real-world applications, from spam detection to predicting stock prices. At the heart of supervised learning is the concept of a training set, a collection of input-output pairs used to train the model. The model's objective is to learn a function that maps inputs to the correct outputs. This learning process is facilitated through the minimization of a loss function, a mathematical representation of the error between the predicted and actual outputs. Common loss functions include mean-squared error for regression tasks and cross-entropy loss for classification tasks. These loss functions guide the optimization process, typically carried out using algorithms like gradient descent, to update the model's parameters iteratively. A practical tool that exemplifies the application of supervised learning is scikit-learn, a robust Python library that offers simple and efficient tools for data analysis and machine learning. Scikit-learn provides a wide array of algorithms for both classification and regression tasks, including support vector machines, decision trees, and ensemble methods like random forests. These algorithms can be easily implemented in a few lines of code, allowing professionals to focus on fine-tuning models to suit specific needs. For instance, random forest classifiers are highly effective for handling datasets with numerous features and are resilient to overfitting, making them a popular choice in scenarios like medical diagnosis and fraud detection. One of the critical challenges in supervised learning is ensuring that the model generalizes well to unseen data. Overfitting, where the model learns the training data too well, including its noise and outliers, is a common pitfall. Techniques such as cross-validation are employed to mitigate overfitting. Cross-validation involves partitioning the dataset into subsets, training the model on some subsets while validating it on others, and iterating this process to ensure that the model performs consistently across different data splits. This approach helps in selecting the best model and fine-tuning hyperparameters such as learning rates and regularization strengths, which control the complexity of the model. Another practical framework for implementing supervised learning is TensorFlow, an open-source platform developed by Google. TensorFlow's high-level API, Keras, simplifies the process of building and training neural networks. These networks, particularly deep learning models, have dramatically advanced the field of supervised learning, enabling breakthroughs in areas like image and speech recognition. For example, convolutional neural networks, a type of deep learning model, are adept at capturing spatial hierarchies in visual data, making them indispensable for image classification tasks. In practical terms, TensorFlow provides pre-trained models and transfer learning capabilities, allowing professionals to leverage existing models and adapt them to new tasks with limited data, thus saving time and computational resources. Supervised learning's effectiveness is further illustrated through case studies. For instance, in the healthcare industry, supervised learning models have been used to predict patient outcomes based on historical data, improving decision-making processes and patient care. A study published in the Journal of Medical Internet Research demonstrated that machine learning models could accurately predict hospital readmissions, enabling healthcare providers to intervene proactively. This case highlights the transformative potential of supervised learning in creating actionable insights that drive better outcomes across various sectors. The choice of algorithm in supervised learning depends on the problem at hand and the nature of the data. For linear relationships, linear regression and logistic regression are often sufficient. However, for more complex patterns, nonlinear models such as decision trees and neural networks are more appropriate. Decision trees, for instance, are intuitive and easy to interpret, making them suitable for applications where model transparency is crucial. On the other hand, neural networks, particularly deep learning models, excel in capturing intricate patterns in large datasets, albeit at the cost of interpretability. The success of supervised learning also hinges on the quality of the data. Data preprocessing steps such as cleaning, normalization, and feature engineering are critical. Feature engineering, the process of selecting and transforming variables to improve the model's performance, is especially important. Tools like Pandas, a Python data manipulation library, facilitate efficient data preprocessing, allowing professionals to clean and prepare data for modeling effectively. Feature selection techniques, such as recursive feature elimination and principal component analysis, are also employed to reduce dimensionality and eliminate irrelevant features, thereby enhancing model accuracy and computational efficiency. Moreover, the evaluation of supervised learning models is a crucial step in the development process. Metrics such as accuracy, precision, recall, and F1 score provide insights into the model's performance, particularly in classification tasks. For regression models, metrics like R-squared and mean absolute error are used. Evaluating models on a validation set, separate from the training data, ensures that the model's performance is assessed on unseen data, providing a realistic measure of its generalization capability. The integration of supervised learning with real-world applications continues to grow, driven by advancements in computational power and the availability of vast datasets. For example, in the financial sector, supervised learning models are employed to assess credit risk, detect fraudulent transactions, and manage investment portfolios. According to a report by McKinsey & Company, machine learning techniques, including supervised learning, have the potential to generate value worth $1 trillion annually in the global banking sector alone. This statistic underscores the significant impact that supervised learning can have on industry, highlighting the importance of mastering these techniques to remain competitive. In conclusion, supervised learning is a cornerstone of machine learning paradigms, offering a structured approach to learning from labeled data. The principles and techniques of supervised learning, from selecting appropriate algorithms and pre-processing data to optimizing models and evaluating performance, are critical for professionals aiming to harness the power of AI. By leveraging tools and frameworks such as scikit-learn and TensorFlow, practitioners can effectively implement supervised learning models to address complex challenges across diverse domains. As the field continues to evolve, staying abreast of the latest developments and best practices in supervised learning will be essential for professionals seeking to enhance their expertise and drive innovation.